Today you'll be graphing square root and cube root functions. Okay, so a radical function is in the form f of x equals the nth root of x. A square root function, f of x equals the square root of x, is the most basic parent function of f of x equals a, the square root of x minus h plus k. And the most basic one is obviously the square root of x. And when you're choosing values for your xy table, you always want to choose things that are perfect squares. And when I plug 0 in for x, square root of 0 is 0, square root of 1 is 1, square root of 4 is 2, and the square root of 9 is 3. So what we'll actually do now is we will plot those points. So as you can see, we've plotted the points, and so now we're just going to draw a nice curve, and that's all you have to do. Oh, you will have to do domain and range. So our smallest x value, we notice here, is the y-axis. So my domain is going to be 0 to infinity, and we can take the square root of 0, so we include it. Our range, or smallest y, is also on the x-axis. So our range is also 0 to infinity. So it's been a while since we've done graphing, so we're just going to review the different shifts and things of that nature. So notice we're going to graph y equals the square root of x minus 2 and y equals the square root of x plus 3 with our parent function. Now we've graphed the parent function earlier, so I'm just going to put it on our current grid. So notice we've just graphed y equals the square root of x. So remember, we're going to look at our different shifts, and I'm going to do an xy table, and then we'll, do our thing. Okay, so remember we can only do perfect squares in for x to get a whole number answer, so we're still going to use 0, 1, 4, and 9. And remember, when we fill in our xy table, it's like we're doing the square root of 0 minus 2. Well, that gives us negative 2. The square root of 1 minus 2, that will give us negative 1. The square root of 4 minus 2, that's going to give us 0. And the square root of 9 minus 2 will give us 1. So what we're going to do now is we're going to plot those points in graph and see what happens. So if we look at our graph, notice it just moved our parent function down 2. Okay, so now we're going to do something similar with the other function. If we come back over here, we can write underneath our xy table that it's shifted down. Now, when we do our other function, y equals the square root of x plus 3, we're still going to use those same perfect squares in for x. So we have the square root of 0 plus 3, that is 3. The square root of 1 plus 3, that is 4. The square root of 4 plus 3, that's 5. And the square root of 9 plus 3 is 6. So we're going to plot those points, and we're going to see what happens. So notice what happened to our red parent function, y equals the square root of x, with y equals the square root of x plus 3. Hopefully you recognize that it shifted our function up 3. So now it says, how is this similar to graphing absolute value in quadratics? Okay, let's take a second and think. Okay, so hopefully you've said if k and y equals the square root of x plus k is positive, it's going to shift y equals the square root of k up k units. If k is negative, it's going to shift y equals the square root of x down k units. Next, I want you to take a minute or two and try the 2 example u-tries. See if you can do it. Okay, so hopefully you found y equals the square root of x plus 2 to be shifted up 2 on the y-axis, and y equals the square root of x minus 4 shifts the parent function down 4. Now let's look at another problem. First thing I'm going to do is I'm going to put my parent function on my graph. So notice we have our y equals the square root of x graphed. Us to discover the shifts in y, or f of x equals the square root of x minus 2, it is a little trickier because the shift is underneath the radical. So I'm thinking in my mind for this first time, what value, when I substitute in for x, I get the square root of 0. And hopefully you recognize that it's 2, because the square root of 2 minus 2, well, that's the square root of 0, which is 0. What value of x is going to give us a positive 1? hopefully you recognize that's 3. The square root of 3 minus 2 is the square root of 1, which is 1. What value of x is going to give us the square root of 4? Well, what number minus 2 equals 4? That would be 6. That's going to give us 2. And then what value of x is going to give us the square root of 9? Well, 11 minus 2 is 9, and we know the square root of 9 is 3. So we're going to plot those points and see what happens. Okay, so hopefully you've noticed that the function y equals the square root of x minus 2 just moves our function y equals the square root of x to the right, 2. So if we look at the other example, y equals the square root of x plus 6, I'm thinking the same thing. What value are we going to replace x with so that we have the square root of 0? Well, we're going to use negative 6. The square root of negative 6 plus 6 is the square root of 0, which is 0. What value of x is going to give us 1 whole? Well, I know 6 minus 5 is 1, so I'm going to use negative 5. Right? The square root of negative 5 plus 6 is going to give us 1. What value of x is going to give us the square root of 4? Well, 6 minus 2 equals 4, so we're going to use negative 2. The square root of 4 is 2. And then what value of x is going to give us the square root of 9? Well, I know 3 plus 6 equals 9, so we're going to replace the x with a 3. So now we're going to plot those points and see what happens. So hopefully you've recognized y equals the square root of x plus 6 just moves the parent function to the left 6 units. Okay, so how is this similar to graphing absolute value in quadratic functions? Well, in y equals the square root of x minus h, when h is negative, y equals the square root of x moves right h units. When the h value is positive, it's going to move the parent function h units left. Remember, this is like when we did absolute value in squared functions. If the value is inside with the variable, in this case under the radical, it's going to do the opposite of what we're thinking. But it's the same as absolute value in quadratics. Yay! Now I want you to take a minute or two and try the next example you tried. Okay, so hopefully you have a graph. The first function, y equals the square root of x minus 4, shifted to the right 4 units, whereas y equals the square root of x plus 3 is shifted left 3. Let's look at another problem. So notice we're going to graph y equals the negative square root of x and y equals negative 1/2 square root of x on the same coordinate plane as the parent function. So the first thing we're going to do is plot the parent function, y equals square root x. And we have our thing. Okay, so to help us remember what's going to happen in y equals the negative square root of x, we're going to use our still perfect squares because there's nothing underneath the radical. Notice we're going to have negative square root 0, which is 0. We're going to have negative square root 1, which is negative 1. We'll have negative 2 and negative 3. And let's notice what happens. So when we plot these points, remember if I have a negative in front of the radical, it's going to reflect over the x-axis. And remember for y equals negative 1/2 square root x, because there's no restriction underneath the radical sign, right, it's just an x, I'm just going to use our perfect squares. So notice we'll have 0, we'll have negative 1/2 times the square root of 1, which is negative 1/2. We'll have negative 1/2 times the square root of 4, which is negative 1/2 of 2, which is negative 1. And we'll have negative 1/2 of the square root of 9. This will give us negative 3/2. Let's plot those points. So notice for y equals negative 1/2 square root x, it still reflected the y equals square root x over the x-axis. And remember, if the number in front of the radical is between 0 and 1, we call that a vertical shrink or compression. If the value is larger than 1, then we call that a stretch. Okay, so remember in f of x equals a square root x, when a is negative, it's reflected about the x-axis. If a is between 0 and 1, we call that a vertical compression or shrink. And if a is greater than 1, it is a vertical stretch. It is the same as absolute value in quadratics. Now I would like you to take a minute or two and try the example you tried. Hopefully you get this graph. So the y equals 3 square root x is the vertical stretch of y equals square root of x by a factor of 3. So notice when we talk about cube root, when we want to graph f of x equals the cube root of x minus 4 and g of x equals the cube root of x plus 5 on the same coordinate plane as the parent function. So this time we're going to want to choose perfect cubes so that we don't, we can graph whole numbers. We know the cube root of negative 8 is negative 2. The cube root of negative 1 is negative 1. 0, cube root of 1 is 1, and the cube root of 8 is 2. So let's graph and see what this looks like. So we know we have 0, 0, 1, 1, and 8, 2. We also have negative 1, and negative 8, negative 2. And here is what our graph looks like. Now, if all of our shifts for absolute value, for quadratics, and for square root were the same, what do you suppose for cube root all of our shifts are the same? They are. So remember, if minus 4 is outside of the radical, this is an up or down shift. So negative 4 would be a down shift. So I'm going to move all of our parent function points down 4. For g of x, we're going to move the parent function up 5. So notice our shifts were the same, and this is our graph. If we look at the next example, we're going to graph y equals the cube root of x minus 5 and y equals the cube root of x plus 2 on the same coordinate plane as the parent function. So let's sketch the parent function first. So now that we've graphed our parent function, we can graph our translated functions. Remember, if the number is inside with the x, it's going to be a horizontal shift, and it's always opposite of what you're thinking. So the minus 5 means we're actually going to shift the parent function right 5. And our translated function shifted to the right 5 is as follows. Now let's do the other one. So remember, if I have the cube root of x plus 2, it's opposite of what we're thinking. So we're going to shift the function left 2. And there you go. There's our graph. The end. If we look at the next example, notice we're going to do a stretch and a compression on the same coordinate plane as the parent function. So let us graph y equals the cube root of x first. Now that we have sketched our parent function, now we can look at our shifted functions. So for f of x, y equals 2 cubed root of x. Unfortunately, there really is no shortcut. So what you will have to do is essentially do an xy table, which is fine, we don't mind. Remember, you're going to choose perfect cubes to go in for x. And we know the cube root of negative 8 is negative 2 times 2 is negative 4. The cube root of negative 1 times 2 is negative 2. We'll have 0. The cube root of 1 times 2 is 2, and then the bottom will be 4. Now let's graph those points and notice what happens. So notice when we graphed our points from the xy table, we have a vertical stretch, right? The graph appears stretched further than it was. For g of x, we're going to do exactly the same thing. We are going to make an xy table and choose perfect cubes to replace x with. So we'll still choose our negative 8, our negative 1, our 0, our 1, and our 8. We know the cube root of negative 8 is negative 2 times 1/2 would be negative 1. The cube root of negative 1 times 1/2 is negative 1/2. We'll have 0. The cube root of 1 times 1/2 is 1/2. And the cube root of 8 is 2 times 1/2 is positive 1. Let's graph these values and notice what happens. So notice for g of x equals 1/2 the cube root of x, our graph got closer to the x-axis, so that is our vertical compression or shrink. Okay? So notice what we have here in the tables. We have our parent functions listed for square root and cube root. We have our translation, horizontal by h, vertical by k, and we have our essentially vertex forms-ish. Remember, if it is negative in front of the radical, that is a reflection about the x-axis. A stretch if a is greater than 1, and a shrink or compression if a is between 0 and 1, or a reduced fraction. So now we're going to look at some examples that you're going to see on your upcoming formative. So if we look at the next example, we're going to graph y equals 3 square root of x plus 2 minus 4. And remember what we did last semester. We drew a box over a parent function, and we actually graphed y equals 3 square root x first. And because it's square root, we choose perfect squares. And we plug it into our parent function. So we know the square root of 0 times 3 is 0, the square root of 1 times 3 is 3, the square root of 4 times 3 is 6, and the square root of 3 times 3 is 9. And we just are going to plot those points. The next step is to take care of our shifting. So notice this minus 2, that means left, and the minus 4 means down. So we're just going to move all of our points left 2 and down 4. And there's our graph. The next thing you'll have to do is find the domain and the range. Well, our smallest x value in our translated function is -2. So we'll start off with -2, and it goes forever increasing to the right to infinity. And for the range, our smallest y value, remember y's are this way. So our smallest y value is located here at -4. So our smallest y is -4 to infinity, okay? And that's all you're going to need. The other problem you will have to graph is a cube root function. Okay, so the first thing you'll do is you will put a box over your parent function. So it looks like we're going to graph the cube root of x. Let's plot those points now. Once we have our parent function plotted, what we can do now is we can look at our shifting. The plus 3 is outside of the radical, so that means it's a translated shift. It's going to go up 3. That's a u. So we're just going to move all of those dots up 3. And then draw our curve. And then all that's left for us to do is the domain and range. So because I can put any number I want into a cube root, negative or positive, our domain is just going to be from -infinity to infinity. And so will our range. And that's all done. You are officially ready to do some practice. The end.